In this video, let us talk about Q meter, which is measuring quality factor. So whenever we deal with the quality factor, it is also called a storage factor. It comes into picture when we are using passive elements that are inductor and capacitor. They are basically energy storage elements. Their objective is to store the energy in one half of the cycle and return it back to the supply during the next half of the cycle. They do not basically dissipate any energy ideally, but practically the inductor and capacitor also contains some small amount of internal resistance due to which they may dissipate the energy. So, quality factor basically measures the efficiency of the inductor or capacitor. The definition is reactance to resistance ratio. It is given by XL by R or XC by R in case of capacitor. So, lesser the value of internal resistance, higher will be the quality factor. So, if higher is the quality factor, more efficient is the coil. So this is the practical significance of quality factor of any coil. So now we'll have to measure this quality factor of an unknown coil. That will be done by Q meter. So before that, let us go through a series RLC circuit which is driven into resonance state. So let us understand what basically happens at resonance condition. So we have RLC connected in series with the source. So if we try to write the expression for EL, which it will be VR plus VL. VR is voltage across resistor given by I into R. VL is voltage across inductor given by I into XL. VC is voltage across capacitor or EC given by I into XC. So the net impedance of the circuit is Z equal to root of R square plus XL minus XC whole square. Whenever the circuit is driven into resonance condition, at that point of time, all the energy stored in the inductor is transferred to the capacitor, and the energy stored in the capacitor is transferred to the inductor. So this is what basically happens. At this point of time, XL will be equal to XC. So the net impedance will be equal to the resistance. So the resonance is a condition, only condition where the reactance of the inductor will be equal to capacitor. At that point of time, net impedance will be equal to R. Already you have studied this concept in your basic electrical engineering. So we'll be using that here in the Q meter. So this is the corresponding phasor diagram. So whenever it comes to the quality factor, we know it is defined by XL by R or XC by R. Let us try to multiply and divide by I. So you have IXL by IR, IXC by IR. So IXC from the circuit, you can see IXC is nothing but EC, IR is nothing but E, because at resonance IR is same as E. So it is given by the ratio of EC by E. That is, if we know the voltage across the capacitor and the source voltage, their ratio will give us the quality factor. So this is the idea behind Q meter. So I repeat once again, ratio of capacitance voltage divided by source voltage will give us the quality factor only at resonant condition. So now let us go to the practical Q meter instrument. Here we have an oscillator which acts as a source, and we have a thermocouple voltmeter which is represented by a heater, and then a transducer is present here. Unknown coil is present at this point, which is a combination of R and L in series. This is connected between the test terminals T1 and T2. Capacitor CD acts as a stray capacitance, which is imaginary in nature. That means its effect is present, but physically there is no capacitance there. We have a resonating capacitor, which is a variable capacitor, and we have the voltmeter here, which is termed as circuit Q meter. So across this voltmeter, we measure the capacitance, which is EC, and then we measure E across the thermocouple voltmeter. So coming to the oscillator, it usually operates in the range of 50 kilohertz to 50 megahertz. In this particular case, Then, as I explained just now, shunt resistance is of very low value, such that the thermocouple reads E. We very well know that thermocouple is an instrument which converts heat into equivalent temperature. So whenever source is given to the heating element of the thermocouple, it generates heat energy that will be converted into effective voltage E. Now, as usual, at resonance, Q is given by EC divided by E. XL is equal to XC. XL is nothing but 2 pi FL. XC is 1 by 2 pi FC. So we get F as 1 over 2 pi root LC. This F is nothing but the resonance frequency, or the frequency at which resonance is said to occur. So here, what basically happens is we try to measure EC. We have the value of E that is already measured. So if you take the ratio of EC by E, it will give us the quality factor of this unknown coil that is connected. This is the operation of practical Q meter. Next, we'll be studying errors in Q meter. So coming to the errors in Q meter, the first one is the measured quality factor, error due to measured quality factor, and error due to distributed capacitance is the second one. So let us see these two errors. So coming to the measured quality factor, basically if you see the practical Q meter over here, the unknown coil is connected in a tank circuit having R and L in series. Along with that, we have R shunt over here, which is a part of thermocouple. So due to this R shunt present in the tank circuit, it will result in error in measurement, because significant amount of resistance of this also will get added with unknown coil resistance. That will introduce error in the measurement. So if we take Q measured, the quality factor that is actually measured will be XL by R plus R shunt. But actually the Q value that has to be measured expected is XL divided by R. So Q that is measured is XL by R plus R shunt. Q that is expected or actual is XL by R. Let us take the ratio of actual by measured. We have 1 plus R shunt by R. So this can be rearranged so that we get Q actual is equal to Q measured into 1 plus R shunt by R. So if R shunt is as low as possible, then Q actual will be equal to Q measured. So lower quality factor coils having high resistance results in low value of R shunt by R and error is negligible. That is, the coil having lower quality factor, the error will be negligible. Coil having higher quality factor, error is serious or sensitive. Next, let us go to error due to distributed capacitance. So here, as I told you earlier, distributed capacitance is nothing but stray capacitance. That means physically capacitance as an element is not present here, but the effect of capacitance will be present over here. This happens when two conducting elements are separated by space. Then virtually effect of capacitance will be there. So here that is represented by CD. It is acting across the RL combination. We have the oscillator. We are having a capacitor which is a variable capacitor over here called as tuning capacitor, and as usual we have the circuit Q meter. Initially we try to set the tuning capacitance to maximum value C1. That is, we try to set the capacitance to the maximum value, and that value is nothing but C1. And then by varying the source frequency F1, resonance is achieved. Resonance is said to be achieved when F1 is equal to 1 over 2 pi root of L into C1 plus CD. Resonance is said to occur whenever this frequency is reached, or when this expression holds good. Resonance is achieved. So this is the relevant expression. Then the frequency is varied, that is the new frequency. See, F1 is the frequency corresponding to tuning capacitance C1. See, initially we set some value of C1 and adjust the F1 to reach the resonance condition. Now later on, we try to vary the frequency and attain a new value of frequency which is double of the initial frequency. So F2 will be equal to twice F1, and capacitance now will be varied to achieve resonance. That is, initially we had kept capacitor constant. By varying frequency we achieved resonance. Now keeping frequency constant, we vary capacitance to achieve resonance. But the new value of capacitance is double of the original frequency, and then the once the resonance is achieved, the new value of capacitance that has brought in resonance is C2, and the expression is F2 is equal to 1 over 2 pi root of L into C2 plus CD. We know that F2 is equal to 2F1, so let us equate the same. This is the expression for F2 and this is the expression for F1 multiplied by 2. So if we simplify this, we get CD equal to C1 minus 4C2 divided by 3. So distributed capacitance is given by C1 minus 4C2 divided by 3. So this is the error due to distributed capacitance. So Q actual, if we try to get the Q actual, it will be equal to Q measured into C plus CD divided by C. So this is nothing but we are talking about error due to distributed capacitance. In the next session, we'll go for applications of Q meter.